All right, picking up where we left off, what I'm going to do here is we're going to pretend that this doesn't exist, and we'll just start working with this stream that's over here since we already have simulation that's written out. Now, you'll be asking, why am I binding a high-resolution simulation back to something that is already pretty high resolution? There's a couple of reasons. One, like I said at the beginning of the lesson, is this is a more traditional workflow where you actually would be binding something to a lower resolution simulation or simulation data that's different than your actual renderable geometry. The other reason here is I wanted something that subdivides cleanly, and triangles don't necessarily subdivide that cleanly, whereas quads do. So I wanted to bind a quad mesh to this triangulated mesh. As I said earlier, you could totally do the simulation just with quads if you wanted to, and then you wouldn't have to do this step at all. Or you could just render this triangulated geometry if you wanted to, but it's a bit ugly looking, right? There's a lot of weird folds and things happening that you would want to clean up in rendering. So here's how I did this step. We basically duplicate the network that we had up here. So I've got one grid, and I am referencing the size of that grid to this grid over here. So as this grid changes size, this grid will change size too. I'm applying UVs to this so that we can actually put textures on it if we wanted to. Here I'm just using a UV texture node, and I'm projecting it on the y-axis. You can change your other axes, but it won't make sense because your geometry is a top-down view, and you want to apply UVs looking straight down at it. We're copying the exact same way that we did before with the same values. And again, I have that layer attribute on here, and I'm promoting it. Now, I did one additional thing here. I put an assemble SOP down. An assemble SOP is useful for looking at disconnected pieces of geometry and naming them. So if I go into my spreadsheet here and we go into the primitives, you'll see now that there's this new attribute called name. And as we scroll down, we have piece 0, piece 1, and piece 2. That attribute name here is controlled by this prefix. So if I change this to cloth, you'll see that changes to cloth. So this is useful because we'll want to be able to target each of these separately in rendering if we choose to. Now this is where some of the magic comes in, is I want to deform this with that cloth simulation. And to do this, I'm using something called a point deform. Let's take a look at how this works. Point deform will want to take in the mesh that we're deforming. So that's going to be our high-res piece of geo. And then it's going to want to take in something called a rest point lattice. What the rest point is it is the starting point, the flat state, the state that most matches here from our deforming mesh, our high-res, our simulation mesh. Well, we never stored anything called a rest state in here. So how are we going to get that? The way that we're going to get that is we are going to tell our cached simulation object here, please just grab frame number 1, which we know is the beginning of the simulation. So to do that, we will use a time shift. We'll pipe that right in, and we'll delete this expression out of here. So delete the channels, and we will manually type in frame number 1. So that gives us frame number 1 of that mesh, and we'll put that right in here. Then it's going to want the deforming mesh. So for that, we're going to get the live current frame value, and we'll put that in. And now when I enable that, we're getting this nice deformation. Now, one thing that can get confusing with this is that it uses a distance method. It says like, well, how close is that point of the mesh to where I am? And then I'm going to choose which point to deform it with. But it's not really matching the pieces up with individual pieces. And sometimes that can get a bit messy. Luckily, we have a piece attribute that we can use in here. So we have a layer attribute. That's one of the reasons why we did layer attributes in both of these, and I can use that to help the deformation here. You might not notice anything happening here, but Usually you will. And then finally, you can adjust the maximum points that influence this deformation and the maximum radius that it will look for in here. Now, if I look at my other settings, I think I changed this to 20 maximum points and dial the radius down. So let's take our maximum points and we'll dial that down to 20, and our radius dialed down a little bit. You can see a little bit of a difference there, right? You can dial this up or down. This is sort of a season to taste kind of thing. And you can play with all of this stuff. Whatever works for you. Right? You'll notice once you start dialing a radius too high, right, you can see how the influence works. More points are influencing each of these points. So we have 100 points influencing what happens to each of these points, and the results get a bit more diffused, a bit more evened out. So if I dial that down to 20, right, you'll see we have less points influencing. So the results are a bit closer to what we actually simulated. And so there's a reason why I had this 0.05 and 20. So you'll notice a lot of those interpenetrations went away when we did that. All right, finally, we need to put normals on our geometry because we have no normals here. Anytime you're going to render a piece of geometry, you're going to want normals on that. So I'll put in normal SOP down here. That will give us geometric normals, and I believe I have just default values in here. We also have no velocity information, so that's going to be useful to us when we want to render motion blur on here. For that, I am using a trail SOP. So a trail SOP has an option in here called compute velocity, and all we need to do is wire that up, and we get a velocity attribute which we can use for rendering. That gets stored on our geometry. So you'll notice that we branched off here. As I mentioned before, I wanted to make sure that this subdivided cleanly and that I like the results of that. So just for testing purposes, I put down a subdivide node. I could see that it looks nice and smooth. I'm liking the results, but I don't want to write this out to disk because I would like a render engine to do the subdivision at render time. And then finally, I can write that all out to disk. So I do it the exact same way I did before. I don't have any unneeded attributes on here, so I can keep this just as is. We write it out to disk the exact same way we did before. Click Save to Disk, and it will load back in once it's rendered. And now you'll see that we have this simulation now written to disk. This is actually what we will be rendering. And that I have piped into an output, which will be picked up from the Solaris and LOPS context, which we'll get into right now.